Capable. Hey guys, I need to see page 149 in our textbooks. Yep, should have. Okay, you were doing the acupuncture thing listed yesterday? Put that note on. Is that the work with us? Yes. Put your name on there. Guys, make sure your name is on this sheet. Let's turn it in, please. Come on. Ma'am. What do you mean? You're supposed to No, I just said 4 numbers 1 through 7. Change those directions. You're supposed to do the whole thing. There's no way that's not to do the whole. Hey guys, I need to see page 149 out. Need to see page 149 out. Okay, the homework assignment. Hey, how's it going? Hand to me during class. Okay, put your name on it. The homework assignment was still given out on Wednesday, not yesterday. Okay. So I need to see page 149.
Mr. King.
Yes, ma'am.
You forgot my paper.
Alright, do I have everyone's assignment from yesterday? Who do I not have? Let me see what you got at least.
Oh, it ain't.
You didn't do anything?
I wrote a 2 word.
You just hoping I wasn't going to collect it?
I knew you was going to delete that.
What did you do for 90 minutes in class?
I didn't know.
The directions are on there. You had people in your group to work with.
I only had one person in my group yesterday.
You could have worked with that one person. Alright. So, let's get started with the bell ringer first. Alright. The question was, how many zeros will g of x equals x squared plus 4 times x minus 4 times 2x minus 8 have? And what types are they? So several of us said 3, a few of us said 4 though, and a couple of us said 2. So let's start with the 2. Okay, so Hayden or Eliza, why were y'all thinking 2 here? Yes, sir.
I put 2, but that was 2 squares. I thought.
So you're talking about the square right here? Yeah. Okay. So that x squared would indicate how many zeros? 2. Okay. So then why did some of us put 3 and some of us put 4? A wild guess. No, we don't want wild guesses. No, ma'am. Go for it, Marcus.
I put 2 because you got the 2 square roots and you got the 0 and 0.
So what you put 2 as your answer?
I put 4.
You put 4 because you're saying there's 2 here, and then 1 here, and 1 here? What do y'all think about that? Not sure? So one thing I want to point out is, and we have to be careful about this, there's a difference between when it's in standard form versus when it is in factored form, and that's something we have to pay attention to. A small detail to think about is this. If I take x squared and I multiply it by x, what do I get? Because that's what's happening here, we're multiplying. X squared times x gives me what? X cubed. And then I'm multiplying by 2x, which gives me what?
2x, 4.
Right, I have 3 x's being multiplied here. Multiplying by 1 more x, so we get x to the 4th. When I go to standard form, which would indicate how many zeros? 4. We need to notice in that factored form is the idea of dilations. The other thing I would point out is this. Think about each of these factors, which is what Jamarcus did, and I want to emphasize and point that out. When I look at x squared plus 4, by the way, we're right? Elijah's 100% correct. That has how many zeros? 2. Does anybody know what types of zeros, though, x squared plus 4 would have? Rakai, we focus? Okay. What type of zeros x squared plus 4 would have? Would they be real? Would they be imaginary? Would it be a double root?
You say x squared?
X squared plus 4. Anybody know how we could find out what type of zeros it has?
Equal to 0?
Can we set it equals 0? Now what would I do?
Extrapolate.
If I'm trying to find zeros, I can set the factor equal to 0. Technically set g of x equal to 0 and then use your 0 product property, but from here now,
Square root.
square root. Now, one, I bring this up because the detail I saw was messing up on the test that I need you to learn from is this. From here, I'm going to rewrite this as the square root of negative 1 times the square root of 4, right? Square root of negative 1 times 4, that is that I, ladies and gentlemen, is not negative 1. I said that time and time and time again. What is I?
Square root.
Square root of negative 1. When I see this I, or the square root of negative 1 right here, I get what? I. And then what is the square root of 4? It is 2. Not the square root of 2. The square root of 4 is 2. And so I would write this as 2i, but do remember, anytime I take a square root, I gotta do plus or minus. So what kind of zeros? Imaginary. Which I will point this out, this should make sense. This is a parabola that actually has a y-intercept of 0, 4. That's also the vertex, and the parabola is going to be concave up. So even though it has imaginary zeros, how many zeros does it have? 2. X minus 4. What would that 0 be? X ends up equaling 4. Now the 2x minus 8 is a little bit tougher, but 2x minus 8 equals 0. 2x equals 8. What does x end up equaling here? So now I get a double root at x equals 4. Now, these are still slightly different because one has a slope of 1 and is just an approximation. The other has what slope? What was the slope for 2x minus 8? What is the slope for y equals 2x minus 8?
Negative 8?
Slope?
Oh, 2.
2, right? Y equals mx plus b. So it looks something like this. So notice how many zeros are here at that double root? 2. How many zeros does this have?
2.
Remember, if it's a parabola, it's what degree? Second degree, and every second degree has how many roots? 2. Remember, that's why we had a plus or a minus here, right? Positive or negative. So how many zeros do we have?
4.
4. I bring all this up and I want y'all to see like there's a pattern here and there's a connection between the equation and our graph. You want to draw out the individual factors to help you end up graphing what g of x looks like, but also we want to notice that the equation and the zeros in the equation will match the graph. When we have it in factored form, you have to identify how many zeros each factor has. What are your questions before we continue today? You have to identify how many zeros each factor has. Going once. Going twice. Alright. So, agenda, quick note about the test. The tests are in the grade book. I was up very late last night after my wife got home and she could help take care of Alex. I had finished grading tests. They are in. I will say there's a handful of us in this class. Talk to me after class. Let's see. I had. Hold up. Here we go. Phoebe, Lily Kate, Treyana, Rakai, and Desiree, Hayden, Tevin, and Shania. I thought that you wanted more time on your test than what you had done. So talk to me after class, and let's find time for you to come in today.
I did.
Did you finish? Still talk to me after class for a minute. Bless you, Mr. Kilpatrick. Good morning, Grace.
Hey, Grace.
And
Okay.
there you go. So, just talk to me after class so we can finish that up. Grace, you too, we gotta figure out your tests. Okay? Yeah, I had a reason why. You happy about your test grade?
Heck yeah.
Okay. So, I want y'all to hear me very clearly on this. The test was hard for some of us. I get that. That was probably one of the tougher tests, like the algebra involved in solving quadratics is a little bit tougher, which is why I gave us more time. I need you to hear me very clearly though. I need you to show me mastery, okay? I hope he's okay with me saying this, but Jose came in with a very defeated attitude. Guys, don't come in with a defeated attitude. If you come in and you grow and you learn these concepts better, and you show me greater mastery on the final, I will account for that. The last unit is not done. Your learning there is not done. If you struggled with the last unit, don't give up. Come into tutoring once I give your test back so that you can learn. And show me mastery. Show me greater understanding on your midterm, and I'll account for that. I will say, like, this is probably one of the best tests we've had, where I think over half of us earned higher scores on our understanding checks based on the test, which means we grew a lot. I had some students going from a 40% on the understanding check to a 90% or higher on the understanding check. That happened, okay? So pay attention to learning and growing and showing me mastery. The other thing I will say is this: I think this unit and next unit are much easier than the units we just did. But we are going to have to move more quickly. So knock it out of the park, come in ready to grow and learn. Ask all the questions you can, because it's not about today, it's about what, Jose? It's not about today, it's about tomorrow, and the day after that, and the day after that. It's showing growth and it's showing learning, and that's what I need you to see, which means we need to engage heavily. We are going to get new groups. Let's do that right now before I forget. Oh, that's what I was going to talk about. Literacy for All. I will be grading Literacy for All this weekend. That's the only thing I have, and I will get those grades in this weekend. Yes. A bunch of you will have. None of those grades are in. Because none. Yeah, if there's nothing in there, it means I haven't graded it yet. Alright, here's our groups. Desiree, Ethan, Z, and Jose in group 1.
Yeah, Z.
Yes. Morris, how did you do all of this just now?
Because I had already did, do what you do, I did.
Okay. Group 2 is Miracle, Marshall, Haley, and Jayla. Group 3, Rakai, Jacoby, Cameron, and Preston. Group 4 is Sanaya, Treyana, Grace, and Lily Kate. Group 5 is Naisha, Jamarcus, Tyson, and Phoebe. Group 6 is Shania, David, Eliza, and Tevin. Group 7 is Mickey, Jalen, and Hayden.
Hey, Shannon.
I gotta go back to next week. Tuesday is Wednesday.
Alright, let's see.
I can't see it.
We have several missing students. Why don't we do this? Jalen and Hayden, find one of the groups that has a missing student. Jump in there just so we can have fewer groups and it's easier to work with everybody. Okay? Alright, so what key concepts have I already told you is going to show up on your test for sure that we just applied in the bell ringer? Fundamental theorem of algebra, which tells us what? Yeah, what does that mean though? Come on, rephrase that. Don't just read it. What does that language really mean? Come on guys, we gotta think, we gotta understand. What does that mean?
Any root that we have may be a multiple of any other root that we.
Okay, so some of the roots may be It's called multiplicities, may have multiples, right? That's a part of it, but come on, think about it some more. Let's start at the very beginning. What has to match? That's what I need you to focus on.
The degree,
The degree
the complex,
and the number of complex roots. When I look up here, we talked through this. What degree would g of x end up being? Degree 4, right?
yes.
And when we looked at this factor, it had what type of zeros? Imaginary. When I looked at these two factors, it only had how many x-intercepts? One x-intercept. So do you know how many x-intercepts g of x is actually going to have? G of x is only going to have one x-intercept. But how many roots does it still have? 4.
4.
The degree and the number of roots match. Even when some of them are imaginary, even when we have multiplicities, the number of roots matches the degree. That's what we're saying. And that's fundamental because if we can identify what the degree is, we know how many zeros there are. If we know how many zeros there are, we know what the degree is. And that tells us a lot. And so we're here, wrapping up just a couple of small details about the behavior of functions at zeros before we get into lesson 3. So this is not your homework. This was your homework. All right, so what function did they start us with? We need to pay attention to this. Oh no, you already did this. That's not your homework. That was the other class. Did we already answer these questions?
Yeah.
Yes?
We didn't do 3, but we did 2.
Okay, so we did not do 3, but we did 2. So let's talk through number 3 quickly and then get to your homework that I already looked at. So when the function g of x is dilated by x minus 2, the new function contains a square factor. Similarly, when the function h of x is dilated by x plus 4, the new function contains a square factor. That's based on B and C from our textbook, which we need to have our textbook open and looking at pages 147 and 148. And we have our textbooks open, looking at pages 147 and 148. You don't have volume 1 with you? There's a whole box of books back there. Go find a volume 1 so you at least have something to look at.
Let's see.
There you go. 147 and 148. But also, tell me that. Well, the graphs that we're looking at are 147. Is why I was saying that. Number 3 says, describe how the graphs of the functions behave at zeros described by square factors. So when I looked here, where do I see in C that square factor, the x plus 4 squared? Where do I see that square factor? Look at the graph. Where do I see my square factor? When it bounces back, right here when there's a what type of root?
Nope.
Double root. We gotta pay attention to that, guys. Devin, I need your hood off, my man. Thank you, sir. So, first off, we should notice that there's a double root as soon as I look at the equation. Because again, and it just talks about this, x plus 4 is being what? Multiplied. So it'd be squared, right? How could I tell there's going to be a double root right here even before I've drawn this red curve? So that's based on the equation. I want to connect that to the graph. You're right, but looking at the graph, how do I know there's going to be a double root there?
Because it's going back up the same spot.
But I'm looking just at the factors. You're not wrong, but I'm looking at these factors here.
They intersect.
They intersect at the x-axis. Both of those factors have x-intercepts of x equals negative 4. So how many zeros are at that one x-intercept? 2. That's a double root. And what we need to notice is that at a double root, it's going to touch the x-axis and what? Bounce off. As soon as I see it touching and bouncing, I know I have a double root. Now, I do want to point this out. It's helpful to notice that it's a double root, but also when graphing and I look to the left, right, I'm going to take the y values here. Are they positive or negative? These? These are positive. The linear factor has what type of y values? Negative, and a positive times a negative is? So that's why it's negative and coming up to the 0. And then I look in between. The linear factor has what type of values? And the parabola? And a positive times a negative is? So if it was already negative, it had to touch and then bounce away. So those ideas go together. You can see the idea that it's bouncing away at the same time. Okay? Now, we need to make the note, how are the graphs of the functions behaving at 0 described by square factors? The dilated function, notice that's the final function, the function after the multiplication. The dilated function does what? What's that dilated function doing at that
Well,
0?
intersection.
It's what? It is intersecting, so is it intersecting by going through, or is it doing something else? It's touching and then bouncing away. We need to notice when it's a double root like that, it's going to touch and then bounce away. The dilated function touches the x-axis and then bounces away. At what type of root is that? At double roots, which we see those double roots at square factors. That's a big idea that we need to notice. But what if we have a linear factor? What happens on the graph when we have a linear factor so that it only has one 0? It has to go through. When it's a linear factor, every time it goes through that 0. Dilated function goes through. Okay? The dilated function goes through the x-intercept or through the 0. Based on what we have seen, what are your questions about that? Now, on this page, I've already glanced at the work that a lot of us did, or that we did. I do want to point this out that it does say predict the shape of each function, and there are there's no scale on these axes. We're just predicting the shape. We're drawing out a quick sketch. But what should I easily and quickly identify from those factors? What do I need first? The roots, the zeros, right? And I get those zeros by letting the equation equal what? 0. And then what key idea should we use here? Zero product property. And a lot of us miss this detail, and this really critical detail. The reason you can use the zero product property is because the only way for a product to equal 0 is if at least one factor equals what? That's the whole idea, is that in order for a product to equal 0, at least one factor has to equal 0. So x equals 0, x minus 10 equals 0, x plus 4 equals 0. And so so there's one 0. What is this 0? 10. And this 0? And guys, there's no scale, I'm just approximating. Here is 0 though, I know that. 10 is probably going to be pretty far over to the side. And -4 would probably, if that's my 10, -4 would be a little less than half. That's it. Right? I've identified my zeros. Yes, ma'am.
Why do you put x equals 0? Like, where'd that come from?
So here, remember, every factor equals what?
You asked me?
Yeah.
Oh, 0.
Right. So x equals 0, x minus 10 equals 0, and x plus 4 equals 0. That is one of my factors. It's being multiplied, isn't it? You go with that or no? You sure? Your words say yes. Your body language says no.
Okay.
Okay. Now, I will point this out. I do still want roughly what these factors look like. What else do you know about these factors?
Slope.
The slope. These are all linear, right? It's x to the first. What's the slope of each of these? 1x, 1x, 1x. And so I'm just going to kind of roughly sketch, right? There's not a scale here or anything. I'm just roughly sketching. I am making these slopes parallel, or these lines parallel at least. And now I can start to sketch what f of x would look like. To the left of this 0, what do I know about f of x? Do I have positive or negative values? Negative. Notice, and I do need to be careful, how many factors are there?
3.
So I need to look at all 3 of them. These are all negative, these are negative, and these are, those are way below the x-axis, they're all negative. And if you haven't picked up on this yet, how many negatives do you need to get a positive? 2. So if I have 4 negatives, it becomes a positive. If you have 6 negatives, it becomes a positive. So how many negatives would create a negative? 3 or 5 or 7. So if you have an even number of negatives, the multiplication is going to become positive, and if it's an odd number, it becomes negative. That's an odd number of negatives. So I know immediately that this is negative. It's got to increase to that 0. Then I look in between my zeros. The next set of zeros. What would the cubic look like here?
Oh.
Huh?
Here we go.
You say up. What do you mean by up, though?
Could they positive?
Like it's just going up for forever?
No.
So it's positive, so it's going to go up, but it's got to come back down. If you're not seeing this, notice the top linear factor is positive, negative, and negative. How many negatives do I have? 2, an even number. So all of those values are positive, but it's got to come back down to the next 0. Then for the next section, just based on the pattern, what's going to happen here? Are the values going to be positive or negative? So we want to notice patterns in relationships. They're going to be what? Negative. Notice how many factors are right here? 1. So it's going to go through. Remember how we just talked about the double roots versus single roots? So it should go down, but then it's got to come back up to the 0, and then probably go through. But check it, right? What's this? These values are positive. And if I take a positive, and a negative, that's how many negatives? And so I get negative values. And then up here, right, if I extend this, positive, positive, and positive. What are your questions about that sketch? Going once, going twice. Sold. Alright. Looking at B with g of x, what do I know about g of x? Or what do I need to identify first? I gotta identify those roots, right? So 0 equals x plus 3 times x minus 3 times x plus 3. Just for the sake of time, please notice, don't do this, but for the sake of time, what are the zeros? X equals negative 3,
Positive 3.
and x equals positive 3,
Negative.
and I get negative 3 again. That's important. Why?
Double.
I got a double root there. Please notice, how many zeros do I have?
Yes.
I have how many? 3.
30.
A lot of us are going to be very tempted, so I'm just estimating negative 3 and 3. Okay? The slope would be what? Roughly 1. Okay, so I'm going to just do a slope here, and I'm going to make them parallel. It's just an estimate. A lot of us are going to be tempted to do this. What's a negative times a negative? By the way, don't draw this. What's a negative times a negative? Positive. So we're going to say positive, and then we're going to say negative, and then we're going to say positive. Hey, but what degree is that function right there? That black one? Look at that black one again. That's second degree. How do we know that? It's quadratic. It's a parabola. But what should it be based on this number of factors? Should be third degree. And that's because, remember how this was a double root? We actually have how many lines right here? We actually have 2 lines here, guys. And so we have to account for that. So when I look to the left of this 0 right here, how many negatives do I actually have? Make sure you pay attention to that. If you have exactly the same line, you have to count it each time, because how many factors do you have? 3. And so all of these values are negative. Great job, guys. Yep. What about in between my zeros? What should I have?
We got command.
What's it going to be?
Negative.
Negative again? Notice how many positives do I have right here?
2.
Okay.
Remember, it's the same line, right? And so, oh yeah, that's a double root, so it should touch and then bounce away. And then it's got to come up to the next 0. And now I have positive times positive times positive. Be careful about that. Notice, what does that look like? Does that look like a cubic? Does that look like a third degree? Thanks, Ethan. Yes, ma'am.
Okay, so right here, where you come up, where do you get that from?
Which part? Like here?
Yes.
The very beginning? So remember, and this is that tricky part. You see how we have x plus 3 and x plus 3? So how many lines are actually right here?
2.
2 of them. So because there's 2 of them, both of these have negative values. And then this linear factor has negative values. And how many negatives do we have? 3 of them. So it's negative coming up to that double root. Does that make sense?
Yes.
Like, it's funky, I get it. But we need to notice it's the same factor, so I have to count it twice, though. I have to count it twice. Now, this is another part where it gets a little tricky. H of x. What should this look like? What type of function would I have here? That first piece. That's a what? Not an imaginary, just type of function. Type of function.
Quadratic.
There we go, quadratic. It's going to have a double root, but my point is that is quadratic. 0 is equal to x squared, and notice 0 is equal to x. So I've got a parabola here, just touching at the origin, and then I also have a line here, also touching at the origin. And so we're actually going to see another type of shape of a cubic, but notice, for a cubic, is it going to just go through like a line does here?
No.
No. Notice a cubic always kind of has this pretty steep piece at the beginning. So a positive times a negative is negative. So it's going to come up steep just like before. And then we're going to talk more about these multiplicities later, but notice how many zeros are actually right here in this one spot.
Oh, 3 of them.
There's 3 of them. Notice there's 2 right here, 1 right here, so there's how many zeros? 3. So it's an odd number of zeros, so it's still going to go through, but it's going to have a little bend to it. That is h of x right there. So we're going to study that more in the future, but the bigger thing to notice is this is just a prediction section. We're going over that. We need to notice, though, positive times negative gives me negatives. Positive times positive. So at the bare minimum, we should have negatives and then positives here, 100%. Please note, all I'm doing is I'm identifying are the y values positive or negative. Don't make it more difficult than that. Okay? Questions, comments, concerns before we focus more heavily just on what a cubic function is. So all we're trying to do is sketch what those higher degree polynomials look like based on the what? By the what? So the y values of the factors, but what do we have, what is it all about? Like, what do we have to identify first? Before we can graph those factors, we need the zeros, we need the roots, guys. You gotta identify those zeros or roots first, right, Justin? You alive over there? Okay, cool. So, here I need y'all to notice we're going to look at cubic functions very heavily. This is the next lesson in the textbook. We're going to talk about the key characteristics of the graphs of cubic functions as well. And we're going to blow through this. You're going to have to study this on your own time, but we're going to do this mostly together because the focus is on creating those higher degree functions, but there's a couple of things where I want you to see the real world context. You are going to have a mathy assignment that is just 2 questions for the most part. There are multiple parts to it, but 2 questions over the weekend that applies these ideas. So, here's the getting started portion, all right? Usually I actually come prepared and have already done this, but what's happening in this problem is you can actually build a little box, okay, by cutting out the corners of a sheet of paper. So let's say I have this rectangular piece of paper right here. I cut out the corners here. Boom. And I'll pick that up later, don't worry about it. Right, I can tell none of y'all were that worried. It's fine. Yeah.
Is the math assignment going to be due Monday?
I was planning on Sunday, but we'll talk about it. Yeah, it's 2 questions.
I go to church on Sunday.
I might have access.
You can do it Saturday. Okay. We can make it due Monday, but we need to get it done. So, as long as, honestly, too many of us don't have it done, have even the last set done, so we need to fix that. But notice when I cut out these corners, I can fold up the sides now, and I've created an open, what?
Box.
Little box, right? So, we cut out the corners of this, and I can create a little box. Well, what do we need to worry about with a box?
It's in flat.
Okay, flat, sorry, let me clarify this. If I'm trying to create planar boxes to be able to put soil and seeds in, what do I need to worry about with this box?
The size.
The size of it. What describes the size of a box? The length, the width, the height. And when I introduce or combine all 3 of those, I get the what of that box? Not all 3.
Perimeter.
Not the perimeter. Starts with a V. Volume of the box, right? How much soil can I fit inside this box to be able to put more seeds? Well, I just cut out a small corner. What would happen if I cut out a bigger corner here? It would get deeper, but the area would get smaller, but the volume's still going to change, okay? So that's what they're talking about here, is we have a rectangular piece of paper that is how wide? 18 inches. How long is it? 12 inches. You can really switch the width and the length. And then notice, we don't know how much we're cutting out corner-wise, We're letting that be a variable because if I change how much I cut out, it's going to change the what of this box, the volume. So let's look at this scenario. So we're cutting out those heights. And so here's what we want to notice. If I cut out 0 from this, what's the height going to be? Right? I haven't cut anything out. So it's still a flat sheet of paper. The height is 0. What's the width going to be then? How much? 18 inches? I haven't cut anything yet. What's the length going to be? 12. And so what's my volume going to be? How do I calculate volume? Length times width times height. Nice. So let's pick up a calculator. Length times width times height. Y'all making this one harder than it has to be though.
It'll be 0.
Say it louder than that. You got it.
0.
This one. The volume is what?
0.
0. Sure. Ask, you can go ask the nurse for some of the nurse passes because I don't have any with me, but make it there, make it back. All right. So the volume there is 0. Now the height. So if I cut out 1 inch right there and I fold that 1 inch up, what's my height of the box going to be? It's going to be what? 1 inch. What's the width going to be?
17.
So close.
19.
Remember, I'm cutting away, right? Why 16? Oh, so you just guess? So guys, remember, I'm going to cut 1 inch here, and I'm going to cut 1 inch here. So how many inches did I actually cut out? 2, so it's going to be 16. And what's the length going to be? 10? Anybody want to push back on or ask a question about that 10? Ethan, where'd you get that 10 from? So, well, yeah, so I cut my height here, and I had to cut my height here, didn't I? So I took 1 inch from here and 1 inch from here for a total of 2 inches. Make sense? You good with that? So what's my new volume? 160. Notice that is in cubic inches. Alright? So if the amount that I cut out is 2 inches, what's my height going to be? 2. What about my width? 14. And my length? What is it? 8. Okay. And what's my volume? 224. You already checked it?
Yeah.
Okay. Can I get verification from somebody? Yes, no, maybe so? Yes, okay. So I want to pause though, because I do want to point out, I never, ever, ever want to just start doing calculations and get lost in the calculations. I always want to look for a what, because I'm studying mathematics. Patterns and relationships. Anybody see a pattern starting to form here?
Yes.
So divide by 2 for the what?
It's
For what? The width and the length?
Yes.
So 12, 10, 8, 6, 4, and 2.
And then you add 1.
Okay, so add 1 on the height, so 3, 4, 5, 6, 7, 8. And so then this would be 6, 4, 2, 0, negative 2, negative 4. I know, that's not possible, we'll talk about it. So this is where we get into the idea of the function versus what the actual real world context would be, and we'll talk about that in a second.
That bottom row is just a generalization. It's just H. It's not
Thank you.
8.
Yeah. You're right. So that's a negative 2 here, and we're going to look at H. So we'll get into that one in a second. So what pattern should we notice about the height, the width, and the length? We notice that we're either adding 1 or subtracting 2. So what should immediately jump to my brain about that pattern, about that relationship? Huh? Say again? Is that linear? We want to notice that it has a constant additive rate of change. That's a linear function if I've ever seen one. And so when I think about the fact that this is linear, and I look at my height for the volume, or for a square of size h, what is the height? Well, the slope is what? 1. So 1 times h. What's the y-intercept?
18. Oh, 16.
Not for this one. Not for the height.
Not for the whip.
What's the y-intercept for that height column? 0, 0, so it'd be 0. We can also just write that then as h. So you can do 1h plus 0 using that y equals mx plus b idea. Or, oh yeah, the square corner length and the height are always the same, so it's just h. So then what about the width? What would I write for the width? My negative 2 x, but remember my variable is h in this case for the height, so negative 2 times h.
Why is it negative 6?
We'll answer that in just one second, but I am still missing a detail from this equation. If this is linear, negative 2 times h
Plus.
plus,
1.
remember guys, these are all linear. Y equals mx plus b. Remember, I need my slope and I need my y-intercept. So Eliza, notice how we're taking away 2 every time this increases by 1, right? And negative 2 divided by 1, right? Change in y divided by change in x, that's negative 2. So negative 2 times h plus 18. I know it sounds gross. So what about for the length? Negative 2
times L.
times, it's still based on h. So one thing to be aware of, what we're saying is the width is equal to negative 2 times the height plus 18. The length is equal to negative 2 times h plus what? Plus 12. So right away, does anyone know what type of function this is?
Yeah, I heard it.
I know.
It's not good.
Children acting like fools outside. Just kidding. It's fine. I'm sure it's like soccer, or not soccer. People on, why are people on the tennis court? They ain't my children. I ain't worried about it. Someone else's responsibility. Okay. What type of function are we going to be dealing with in this case?
Vertex.
Say again.
Vertex.
Say it louder.
Vertex.
You say a vertex? That's not a type of function though. That's a feature of a function. Come on, think about it. We have how many factors?
Cubic.
How many factors? 3. So there's how many zeros? 3, because they're all linear. So it's going to be not cubical, that's the thing in offices, but a cubic. Yeah. All right? So there's 2 things I want to show you about this. We need to notice 3 linear factors, 3 zeros. That's cubic. That's degree 3. But let's find these volume values. I still need the rest of these volumes. What's the next volume? 216? What's next? 160 again? 80? 0? Negative what? 56? And we'll get to that one in a second. So here's something I want to point out. Every polynomial had a pattern or a relationship to it. Linear functions had what rate of change? Linear functions have what rate of change? Not just additive, they were not just repeated, there's a special type of additive. Started with a C. Constant additive. And that's important because remember, with a quadratic, there was repeated addition, but a quadratic had what rate of change? A linear rate of change. Remember, that's 1 degree less. So what rate of change should a cubic here have? So remember, multiplicative is only exponential. So when we had y equals mx plus b, the rate of change was constant additive. When it is a quadratic, the rate of change is linear, y equals mx plus b. So when it is going to be cubic, what rate of change should we think about? Which I would point this out, this is x to the 0, this is x to the first. So the rate of change would be, what's the pattern? X to the 0, x to the first, x to the second. So a cubic that we have here should have what rate of change? Quadratic. Let's check. That's a pattern. To go from 0 to 160, what's happening? Plus 160. All right. 160 to 224.
65.
Just 64. 224 to 216. Subtracting. How much? Good job. 8, guys. That's right. By the way, you know you can just pick up a calculator and do 216 minus 224, and that'll give you the minus 8. Now 216 to 160 means I'll do 160 minus 216 for negative what? Negative 56. 160 to 180. Negative 80. 80 to 0.
Oh, I'm sure.
So I think it's still subtracting, isn't it? And then minus 56. There does not appear to be a pattern there. But we got to keep going because it's supposed to be a quadratic additive. Now, 160 to 64. So just like before, I would do 64 minus 160. What do I get? So my minus or plus? 160.
I'm tripping. No, wait.
Yeah, no, so we're subtracting. Remember, this is why I said do 64 minus 160. So for the next one, I would do negative 8 minus 64. So minus 72. This one, next one's a little tricky. We gotta be careful. So I mean negative 56 minus what?
Negative.
Notice it's a negative 8. So I need negative 56 minus a negative 8.
Negative
48.
Negative what?
48.
Is it negative 38 or negative 48?
48.
Negative 48. Okay? Same thing again. I think it's negative 34 maybe. Does that sound right? 24? Thank you. You're right. Plus 0, and then plus 24. Still nothing constant. But that's okay. We need this to be quadratic additive. So negative 96 to negative 72, that's plus 24.
We don't like have Run write this for the sake of this thing.
I'm just going through this with y'all. You don't have to write it, it's helpful. But negative 72 to negative 48 is plus 24. Plus 24, plus 24. Ah, man, we finally got something constant. If this is constant additive, what is always to the left of constant additive? Linear. So this is linear additive. But notice I still haven't gotten to my rate of change yet. What was to the left of linear additive? Quadratic. So does a cubic have a quadratic additive rate of change? I want you to notice the rate of change is always what in respect to the degrees? The rate of change is always what in respect to the degrees? Come on, guys. What's the degree here? Second. What's the rate of change? What degree? First. Here the degree is first. The rate of change is 0. Here the degree is 3. The rate of change is? The rate of change for a polynomial is always 1 less than the degree. That's a really neat detail that we always want to hold on to because this tells us a lot about the polynomial. the rate of change always has 1 degree less. The rate of change always has 1 degree less. Questions about that pattern? Preston, you awake over there? Cam, you awake over there? Preston, come on. We've got some learning to do. So, number 2 says analyze the relationship between the height, length, and width of each planter box. What are the dimensions of the largest size square? So, when we analyze the relationship, what we want to notice is height, width, length are all what type of function? They're all what type of function? Okay. What type of function? They're what? You want to talk about it multiple times now? We wrote an equation for it because they are all 3 what? Linear, thank you. They're all 3 linear. Okay? That is the first question. What are the dimensions of the largest size square corner that can be cut to make a planter box? Now, be careful about the language. The 2 inches gives us the largest volume, but that's not actually what the question's asking. What's the largest size square that can be cut? And we would still have a box. Hello. I have not seen him. Gotcha. No problem. Sounds good. No problem. Fine. Okay. So look again. What's the largest size cut that we can make? That's the largest volume. I'm asking what is the largest cut we can make? So what did you say? 7. Now that's the last value, but can we actually make a cut that is 7 inches long? Say again. I mean, but if I make 0 cut, then do I actually have a box at all?
No.
I mean, if I go to 6 inches, do I have a box? No. So what's the last cut I can make? 5. So really somewhere in between 5 inches and 6 inches. Remember earlier, Ethan, you were saying, well, you can't have a negative, right? Remember when you talked about that? Guys, you can't have negative length. And so we need to notice, can I keep this pattern going for forever? Yes. Does this pattern work forever in the real world? No. And so this is one of the things that we want to be noticing is that 5 inches is the largest cut, at least based on the table. Because what happens at 6 inches? It's no longer a box. Think about it, guys. 6 inches, isn't that half of the width? Like if I take this box and I cut it halfway in between, do I have anything I can fold up anymore? Here's my half and here's my half. Do I have anything that I can fold up? There's nothing left, right? And so that's what's happening there. And so we want to notice, because at 6 inches, there's not any paper left to fold, right? Pay attention to the real world context. So pay attention to the real world context there. That's an important part, that we use functions in mathematics to represent the real world, but that means that we have to be careful about those functions. You are always going to be smarter than a piece of technology. That calculator can graph the function for you, but can that calculator tell you where you actually have to stop the function because it can't go past that? The answer is no. That's why it's important that in this class we're always trying to learn how to what? Starts with a T. Think. You cannot just rely on plugging and chugging stuff in. You cannot rely on memorizing stuff. You have to think because every real world context is different. But Ethan's immediate gut reaction of, well, Mr. Kinney, I can't have a negative in the real world, those are things we need to notice. That's something we need to immediately pay attention to. Alright, so for number 3 here, I'm going to write it over on this side. What would the function be, right, for the volume? So earlier we said volume is length times width times height, right? So what would my function be? Because I can only have one variable for my function. Do we have a way to rewrite that? Based on information we've already done. Those bottom boxes? What's the first box? The height. What's the equation for the height there? H. Okay? What's something for the width is next? What's something for the width that I can substitute in? And then what about for the height? There is my volume function. Notice that shows even more clearly how many zeros are we going to have. Not trying to trick you. How many zeros is it? 3. Because how many linear factors do we have? 3. And each linear factor has how many zeros? Each one has 1. And we have 3 of them. So we have how many total? 3. Do I need to re-explain anything? We good? Grace is like, I'm here, Miss Kinney, I promise.
No.
You got this. Okay. So here's activity 3.1. This is using the function that we just developed. We talked through it pretty heavily. So we kind of are cheating with number 1 here. I didn't mean to cheat as much, but Louis, Ahmed, and Heidi each used graphing technology to analyze the volume function v of h to sketch the graph. Please notice, that means they did what with this equation in their calculator? Just put it into the graphing portion, right? We're going to have to do this. Mr. Kilpatrick's teaching a lesson on Monday. You're going to have to get used to plugging stuff into the calculator. So go ahead and pick up your calculator, type in that function into the calculator. Now I will point out, can you put that variable h in the calculator?
No.
No, what are you going to have to put instead? Say again?
Do X.
You have to do x in the calculator. Yes, Cam, head up. Yo, where's your calculator? I think you're missing something. You look over there. Okay, come on, pick up a calculator. Marshall, where's your calculator? Why is it on my desk? P.S. By the way, someone chose to walk into my classroom and didn't ask on the day of the ACT and borrow the calculator. If you know where that calculator is, please either bring it back or encourage that student to bring it back. I need these calculators for my students. It's a little irritating.
I know where it's at.
Where is it?
Outside.
Outside?
Yeah.
The school?
Yeah.
Can you please make sure that person brings it back?
Yeah.
Thank you. Alright, so we need to have that equation graphed. Make sure you go to the graph page. Guys, when you go to a graph page and type in that equation to graph it, once you type it in, now, one thing to be aware of, you have to put a multiplication symbol between the x and that first set of parentheses, otherwise it'll give you an error. So you have to put x times. And you're gonna be like, yo, Mr. Kenny, that looks wild. It's okay, we're gonna change the window to it later. Yeah. You gotta remember, you gotta have a graph page. So hit Control and then Dock to add a page. You need a graph page, okay? So guys, just type the equation in for now. I'll tell you how to change, or what to change the window to in a minute. You have to put a multiplication symbol between the x and the parentheses. Guys, you have to put in multiplication symbol between the x and the parentheses. I don't know why the calculator doesn't understand it without the multiplication symbol in there, but it does not. It's something with the way it was coded. Okay? Oops, excuse me. No, don't put the H. Let's do a new document and add a graph. There, there. Yeah, that's what it should look like roughly right now. Make sure you put a multiplication symbol between the x and the parentheses. And just typing out negative 2x plus 18, and then parentheses, negative 2x plus 12. Okay, we'll change the window in a minute. Cam, my man, we got a week and a half left. You gotta make sure you're there for that week and a half. All right, so with this, if you still need help putting that equation in, raise your hand. Mr. Kilpatrick will get there and help you out. So, Lewis, Ahmed, and Heidi use graphing technology to analyze the volume function and sketch the graph. They disagree about the shape of the graph. Lewis says the graph increases and then decreases, so it has to be a parabola. Ahmed says the graph lacks a line of symmetry, so it can't be a parabola. And then Heidi said, I noticed the graph curves back up, so it can't be a parabola. So first off, do you think this is a parabola?
No.
No? Why not?
It can't be a problem.
Some cubic.
It's a cubic, right? Well, what type of function gives us parabolas?
Quadratic.
Only quadratics, or second degree functions, right? So, who is the most correct with their statement? Or who is correct? Heidi is the most correct, but even Ahmed said, hey, it can't be a parabola because there's no line of symmetry, right? Only Lewis was really wrong, but the biggest thing we want to notice is, first off, how do we know it was cubic? What things did we notice already? It's third degree, right? So it is so the graph can't be what? Can't be, yeah, what's the shape of a quadratic though? So it's third degree, so the graph can't be a parabola, because what is a parabola? Because it's quadratic, which is what degree? Second, right? Yes, ma'am. Yes, thank you. Okay. Was I supposed to pass out progress reports in this class? Or is it your third block you're supposed to get it from? Is it this block? If it's supposed to be from first block, I will go down during third block and get the progress reports. So if you're supposed to get it from me, you can come back later today and grab it. If not, if it is third block, just get it from your third block teacher. Okay. So let's talk about this. Please notice for number 2 here, it says to change the viewing window. So the x needs to change to -10 to 15. So this is the x minimum, this is the x max, and then this is the y minimum, and this is the y max. So how are we going to change our window settings on these calculators? What we got to press first? Menu, then what? 4 tells us what? Window/zoom, okay? And then which option allows us to directly change what the dimensions are? Which one? Window settings. So go to window settings. Did you ever get your graph done? Remember, we can't use H, right? So go to your window settings and change your X minimum and maximum based on what's in the book under number 2. So wherever there was an H, we needed an X. And remember, we needed an X in front of this. There you go. For Windows/Zoom, window settings. So X minimum should be -15, X maximum should be 10. Oh no, I lied. -10 to 15. Thank you. So Y min is that -400. Y max is a +400. Okay? Mr. Kilpatrick, you can go around and check to make sure everyone has that. Come on, let's change the X min and max. It's in the, right here in the book, number 2. So notice the first set of dimensions in the book are your X values, the second dimensions are your Y values.
Yeah, right.
-10 to 15. I missaid that at first. Have you done your dimensions? Come on, we gotta get these things correct. Help her out if she's still stuck on that. You got your dimensions, got your dimensions. -10 to 15, not -15. Be careful about that. Okay. That's not even, that's weird, man. Didn't even try to type in the equation. If you didn't even attempt to type in the equation. Yes, sir. Say again. No, as -10 to 15 is a -400 to 40. Oh, no. The X minimum is just the -10. The X maximum is the 15. There you go. All right. Miracle. You forgot your X in front. That was supposed to be right here. That was X times that. Hey guys, it's frustrating when I come around to groups and we have not checked in on each other to make sure that we have the right graphs and the right windows. There's one of me, one of Mr. Kilpatrick, but there are 4 of you, or maybe only 3 of you in each group. Take advantage of your resources around you. Okay. At this point, I'm going to show you a couple of cool features of the calculator. First off, we're going to at least just talk about which characteristics you should think about when you look at this graph. So when I look at this cubic function, what are some characteristics of that function that I should look at on the graph? Zeros, which also are called what? X-intercepts. What other features? The y-intercept. What else? Come on, what else should we be looking at? Guys, we know so many other things.
What did you add, Mr. Cool?
Say again, sir?
What did you add?
Say it louder.
What did you add?
What characteristics should we look at for these graphs?
The zero.
The zeros, we already said that.
Oh, that's what X one.
Say again, Grace. I can't hear you.
Roots.
Roots, we already said that. Remember we said zeros, right?
What were the numbers that you were
Come on, look at this. Like, just look up here. What are some points that we should probably look at? We may not have talked about them a whole lot, but y'all already know these things. Okay, so where the function is positive and negative, that might be important. What else? So positive and negative values. And what we'd say are intervals for that, where the function is positive and where it's negative. Say again. The 3 zeros, so remember, we already said zeros are x-intercepts. Like, come on, all right, watch this. Tell me when I should stop because it's an interesting point of the graph. Okay, so we got our zeros. Tell me when to stop again. Thank you. What is that called right there? Now, it's not a bounce unless it's touching the x-axis and bouncing off. Please note, we only have vertices when we have parabolas. But that parabola, that vertex could be a blank or a blank.
Minimum or maximum?
A minimum or a maximum. So what is this?
Maximum.
That's a maximum. We're about to learn about the difference between what's called a relative or an absolute maximum. But that's a maximum. What other point should we then look at? A minimum. There are some other features we're going to learn about soon, but one of the other features that we have already talked about is where the function, so they're called domain intervals, of increase and decrease. So look at the graph. When I move from left to right, what does the function start doing? It's increasing. Tell me when it stops increasing. I'm going to stop drawing on here. So at that maximum it stops increasing. Notice the maximum is important. Think about a roller coaster. That's where you stop increasing. You start to have fun and go down. Right? That maximum is where it stops decreasing. Or stops increasing. What comes after that maximum then? It's decreasing. Tell me when it stops decreasing. So we have it stops decreasing and starts to increase at a what? Minimum. Those are features we want to notice, okay? So we want to notice that this, and I would write this on there because I believe they have a graph. On the next page in the book, I would go ahead and flip my page over. I would make a note where it has an interval of increase, right? So interval of increase to what point does it stop at? To the what? To the maximum? And then an interval of, what is this? Decrease to the what? To minimum. And we're going to talk about how to write the notation for this soon. And then what comes after this?
Increase.
Interval of increase. And it just keeps increasing forever because there are no more zeros. It doesn't have to turn around anymore. Now, there is actually a key word that I wrote over there that we haven't talked about yet, but is probably one of the most important characteristics. And I wrote it as a part of one of the others. Say again? I didn't write that one up there, but domain and range. What does domain refer to of that function? What does domain refer to for that function? So you can have domains of increasing, decrease, but domain means something very specific. The domain is the set of all, anybody know? Sometimes, for this function, yes, but not always. The next unit we have, we're going to study a couple of functions where the domain is not all real numbers. But in general, domain is the set of all
Whole number?
x values. It doesn't have to be whole numbers. Remember guys, y'all had a mathy assignment on this at the very beginning of the class. If you haven't done that, you need to go back to one of the first mathy assignments where you identify the domain and the range. A lot of times, when we're dealing with polynomials, Naisha, the domain is the set of all real numbers, but it's not always. So, domain is the set of all x values, which, by the way, what do we also call x values? Those are the, remember, zeros are only the x-intercepts. It's not all x values.
Oh, wait.
All x values. Those are what I do what in the function. I substitute them in, so they are called my inputs. Right, so the set of all x values or inputs. That's what we want to think about. So let's contrast that with range. What is that? Set of all y values. Or outputs. There we go. See, those are patterns and relationships, and we're putting a language to those patterns and relationships. Okay? So part B, I'm gonna have to, so notice these are just the features that we want to look at in general. Now we start asking the question, what is the maximum volume of the planter box? Right? Say the dimensions of this planter box. So let's look at the calculator. When I look at this calculator, like I can see roughly where that maximum is, right? It'd be really nice if there was a way to use the calculator to find out exactly what that maximum is. Guess what? There is. What button are we going to press first? Menu. After menu. What did you said 6? Why 6? Oh, it literally says to analyze the graph, right? The calculator is designed to help you out. So what are we looking for when we hit analyze graph? Oh yeah, maximum. That's it. Now, pay attention to these instructions. Right here, all it says is a question of lower bound. You see how that's a vertical line? That vertical line needs to be lower or to the left of your maximum. It doesn't have to be super far to the left, but just a little bit to the left. Use your touchpad to move it a little to the left like I did there, and then hit enter. What question does it now ask? Upper bound, so what does that mean? Scroll a little to the right of that maximum, so it's to the right. And notice how there's a point there that it stops once you get to the right. And then I hit enter. And we need to know how to interpret what this point means. What were the set of inputs again? So that's the interval that we put into the calculator. But what I'm saying is, in the context of the box, what was x? What were my input values? You can go back and look at the getting started to see. That's not what it meant. Like, what is the context of the problem? Go back and look at the getting started. We are trying to find the volume, but was that my input or my output? Yeah, my volume was the output. What was the input? What is that leftmost column? It's the length being cut. Guys, we need to pay attention to the table there. The length being cut. So if the cut is how much? 2.35 what? Yeah, but like what's the units? 2.35 inches. We have a relative maximum, what is this, 228? I'm going to tell you what relative maximum means in a second. Relative maximum volume of 228.2. Volume is inches cubed, right? So that's what you would want to put underneath that problem in the book. What is that, number, or part B? Right? There is a context to these problems. You have to know what the values mean in the real world. Equations and functions in mathematics are not just random things. So pay attention to what your input means and what your output means. And so Mr. Kilpatrick, I think you'll still have enough time for your lesson. You'll still have enough time for the majority of your lesson on Monday, but we're gonna have to finish this up. So because we're gonna talk about the domain and the range and the x-intercepts. But last detail I want to point out is this. I want you to think about this function right here. You see how this arrow continues up? Is it ever going to stop going up?
No.
But in the real world, can you have an infinite volume? No. And that's why it's important to talk about these ideas of a relative maximum. See right here where it stops increasing and it starts to decrease? See how that's the highest point for that area? The highest point for its little area is called a relative maximum. It's not the highest value for the entire graph, but it's higher than everything else relative to it. So, do I have a relative minimum anywhere?
Yeah.
Where? See how that's the lowest. Now, notice, does the graph ever go below that? But is that the lowest point for its little area? So we're going to continue working with this on Monday just a little bit before Mr. Kilpatrick does his lesson. Please note, we have this assignment. I would take a picture of those instructions for that Matthew assignment. If you have finished a Matthew assignment, like I think Ethan emailed me and a couple others, if you finish an assignment late, shoot me an email so I remember to go and look and update your Matthew grades. Yes, you can do it on your phone. It's not ideal, but you can. All right, have a fantastic weekend. Please do everything you can to get this done. When is this assignment due, by the way?
Monday.
Monday, just to help Lily Kate out, but try to get it done before Monday. The sooner you get it done, the better off you are.
Do you usually have a blue
Oh, Lily Kate.
No, that's nice.
There's others too, and I forgot to talk to them a second ago. Yes, you were one of them, right?
It was also really chaotic and
Yeah.
so I didn't want to.
I understand. Okay, so let me pull your stuff up. That's supposed to say four.
I got that. That's opinion. I use the restroom.
Okay. All right. I'm gonna put your stuff down for just a second.
Dang it. These are happy to see you, Mr. Kitty. You are happy to see me.
So, I made some slight notes here. Oh. That's two squares, but here's one square. That's a one square. Right here. So that's on the relation on there. I'll start it back. But that's a 2x squared. Not 4x. Those are very different things. We need a quadratic, right? So I'm going to have you come back. I'll email your question teacher, okay? Through time.
Am I still taking the test?
Okay, so when are you going to come in and fix this?
Is it recording?
So, Monday before school, you're coming in. Is that what I heard? Okay, Monday before school. Yeah. Yes, of course. We will have we have a certificate for you, but I haven't gotten it signed yet. That's my bad.
Okay, that's
And so I'll get it to you. Did you order?